Okay, let's start. We want to do our major work in this course is to do some circuits which amplify. Okay, so we are looking for amplifiers, and as I said last time, both technologies are possible using a BJT or using a MOSFET. We will more concentrate on MOSFET, but as pedagogy or as the word things went through, bipolar came first. So let us give him some credit to it and then go over to MOSFET. So I will not actually show you a bipolar amplifier, I will say okay, if I change from MOSFET equivalent circuit to this equivalent circuit, you can as well evaluate it for bipolars. But before that, let me quickly see the biasing assembly in either cases. So let us say I will do, you have done it, but I quickly want to go through for a BJT. We have already discussed earlier that if I have a circuit which is to act as an amplifier, sorry. I must somehow see that this transistor remains in active mode. So if I draw a characteristics IC versus VCE, which is nothing but V0, and if I write this equation, VCC is equal to IC RC plus VCE. So this is a straight line, this is a straight line. So if I draw this straight line on the same characteristics, it may be somewhere something like this, okay. This value is of course VCC and this is VCC by RC. This is called what? Load line. So if I have fixed the transistor for a given capital IB, that is the base current, over which small IB is going to be imposed, and let us say this is my IB, which is IB dash we may call, then the device has fixed bias current of base which is IB dash, which I can fix, that is what I want to fix. This is the characteristic on which I want to operate for the transistor. IB dash is the base current, IB dash is the base current which is DC current. I want to fix the DC current for the transistor which is on this characteristics, and if I then connect RC on this, then I have a load line like this which intersects this ICVC characteristics at this point, and we know this point is called the operating point or the quiescent point. And for this value, the DC value of VCE we call VCEQ, and this current we call ICQ. These are the DC currents, DC current and voltages at which the device is going to operate for given load of RC. Is that clear? This is called the operating point or the quiescent point. Okay, this is what we want to bias. I want to fix for a given RC, given IB dash, such that I will have now these values fixed. So what is the typical criteria VCEQ should have? I can have a different load lines. For example, I may have a load line something like this, or I may have a load line something like this. What does change? It changes the intersection of load line with the transistor characteristics. That means it can be here or it can be here, or it can be somewhere else, depends on RC I choose. Essentially what is going to change? The value of VCEQ as well as ICQ. If the device has to remain in active mode, what should be roughly where VCE should be always? It should not be close to 0 or small value, because there the device will enter on this side saturation. If I have a very small base current, then the device VB on may not be 0.6 volt and therefore diode itself will not turn on. Is that correct? So I cannot have RC such a value that I have a characteristic somewhere like this, then there is no base current available, there is no transistor action available. So choice of RC must be such that this VCQ should be roughly between, or I should not say exactly, but roughly half of the VCC. So if you keep around half the VCC, it need not be exactly at VCC, VCC by 2, but around VCC by 2, if you get your VCQ, you are ensuring for any value of IB, you will always remain in active mode. So choice of VCQ should be such that you are always in active mode, and typical value should be such that it is roughly half, and don't see if it is 12 volt or 10 volt supply, is it 4 volt, yeah 4 volt is still well within the range of active mode. Okay, so don't insist that it has to be 6 volt, but it can be as close as possible to 50% VCC, it will be ideal for you because it will guarantee your device to remain in active mode. Okay. The reason we are not very much worried is too much because change in IB, which I shown here, is how much it will be, small IB, few millivolts. So that variation in this IB values across this is so small that for the same RC value, change in IC values will be also very small, larger because there is a beta gain going on, so it will be larger than change in IB, but still it will be small enough, but that also should remain within active mode of the transistor. Transistor should not come out of this, and therefore once I said that I cannot have large input signal because it may then swing device to the saturation or cutoff side. Okay. So since we normally will never use larger signals, this course we may not actually work on large signal amplifier, there are issues, there are requirements, but as of now let us say small signal. We must therefore assume that by same logic we will show you later that a MOS transistor, if it has to remain in the saturation which is similar characteristics, it should be half the VDD. Please remember, it is not half is a sacrosanct number, okay, it can be 0.6, it can be 0.4 of VDD or 0.35 of VDD, but it should be away from the linear side and it should be away from the cutoff side. As long as device remains in active mode, your amplification is guaranteed. Okay. So these are the issues when I decide what value of RC I should choose, or given an RC, what VCC if I have given, where I am going to be to find the operating point. This is what we are essentially saying when I say I want to know whether I am in active mode. Is that clear? This is what essentially we say, evaluate VCQ and ICQ. Once these DC values are fixed, we have done small signal analysis. What do we do then? We can calculate GMR, everything value required. Once I know my DC values, I have my everything available on my platter to evaluate the small signal values and therefore small signal gains and small signal whatever we want to. Is that clear? So the idea behind fixing this is very crucial, and therefore it is called quiescent point fixing or amplifier biasing is very crucial for our small signal analysis. Is that clear? The small signal characteristics are governed by the DC or biased DC points, and therefore they should be within your control so that you can fix the other values as per your requirement of the small signal gains or impedances or whatever you are looking for, or bandwidths. Is that okay? So having told the importance of biasing, let us quickly look for an example. There are a few methods in which BJT biasing is done. One of the simplest method, you can see something like this, is to actually connect a resistance RB, and of course there will be RC, okay, this may go to actually VCC, sorry, this is RC, sorry, this is your VCC point, okay, VCC point, and this is your VBE. Let us take a case, VCC is say 12 volt, I have chosen some value, so beta is 100 for the sake of it. And what is VB on, we shall always assume in the bipolar 0.7. What is the criteria we chose, that is the value at which diode will be sufficiently forward, base emitter junction is sufficiently forward biased such that some emitter collector currents are available to us, okay. 0.6 just turn on, 0.75 saturation, so we must remain in between 0.65 to 0.75, which is 0.7, okay. Please actually if you want to evaluate, it may not be 0.7 in real calculation. If you do measurements, you may find 0.69, 0.71, 0.685, don't worry too much. Evaluation is for assuming that it is close to 0.7, okay. Okay, so let I assume 0.7 volt, okay. Now let us say we want this device to have VCEQ equal to 6 volt and ICQ of 1 milliamp. This is the operating point I want to have that, okay. So that is that clear? This is 6 volt is roughly half of the VCC, therefore we roughly know it, we are always in active mode, okay. Then how much is VCE? VCC, no, by formula VCC minus IC RC, VCC minus drop across the load by current IC is the remainder VC. So VCE is equal to this minus drop across RC, is that okay? This voltage minus drop across RC, which is ICRC, must be the remainder is VC, is that correct? And VCQ is what we have been given, but this is the equation we should use. We can also say from this side, let us say current in this is IB. Tell me what is the mesh you are getting from VCC to IB to this to the ground. So anyone can give me another equation, VCC equal to IB into RB plus VB on. So I have one equation here, I have second equation here, is that clear? So if I substitute the values given to me, and how much is IB? ICQ given to me is 1 milliamp, therefore IBQ is 1 milliamp by 100, so it is 10 microamp, okay. Okay, so what is the value we are trying to find from this? I want to know what is the value of RB and what is the value of RC. Two equations, two unknowns, we should be able to evaluate both values. Is that equation? Two equations, two unknowns, everything else is known to us. VCQ is known to us, VCC is known to us, IC is known to us, RC we want to know. Here this is known to us, this we know now, RB we don't know, but this we know. Two equations which are two unknowns, RC and RB, two equations, two unknowns, always solvable. One, find IB value from here, beta times that substitute here and evaluate for IB there, or vice versa. IC by something you substitute here and get the value of RB. So I did this analysis, is that clear? Two equations, two unknowns should be easily solvable, and I get the value of RC, which is typically 6 kilo ohms, okay. And RB I got is 1 mega ohm or 1.1 mega ohm kind of thing, okay. This is a single resistor biasing, okay. Now there is some problem in this which you read in the book, why this is not really preferred biasing. Now one must understand what is the word I am saying, why it is not preferred. Is that point clear? Why will it not be preferred biasing, or why it is something can go wrong with this circuit? You can see IC and IB are related through which term? beta, is that correct? Even actually VB on, both these terms are temperature dependent. VB on may not be that strongly dependent, but I see this beta is very strongly dependent. Beta is also function of IC. The level of IC also decides beta. So if there is a variation in beta, what will happen from this, what will shift accordingly? If there is a variation in beta values, for the same RC RB values you have chosen, what will be moving out? The VCQ and ICQ may not be same as what we actually designed for, is that clear? So this is external environmental dependent, the operating point is not always fixed. Is that clear to you? Is that clear? As beta varies, ICIB will vary accordingly, and you have evaluated for a given value of beta RCRB values, but now they are fixed, okay, but beta varied. So VCQ and ICQ will actually not be same as what they were earlier. This means the device characteristics or device parameter has interfered in your biasing, is that correct? And we will not like this to happen. This is why it says such a, this is, if I say if X variation happens here in denominator, there is another same variation occurs, it cancels. Some, if you say ratioed circuits, okay, whatever vary there, it may also vary here. Also beta is not coming into my final picture of biasing, then I say okay, I have a very stable bias points, okay. Not that any system has that kind of 100% stable points, but closer to this or better than this is what we are looking for. Never say that it is always fixed, it will never be fixed, but how much we can tolerate, how much we should be allowed to tolerate, that the beta value which is IC by IB, small IC by IB there, for the signal we are assuming that should remain constant. Within that range if something is not changing, I damn care what else it changes. As long as the slope there does not change very greatly, I say fair enough, okay. So I should always say in engineering that variation is going to come. How much you should be able to tolerate is your expertise, okay, how good you can get to, okay. Is that point clear? So this is something very trivial, but has to be understood as the analog designers or analog circuit people. Okay, so other method which is most popular fixed bias methods is this. Sorry. Is that okay? Okay, call this RB1, call this RB2. Okay. There are two ways you can solve this circuit. You can solve this circuit, or maybe even third way, which is approximation. What are the two ways I will say? One circuit, one way of doing is around this you apply to the left of this line, what you can apply equivalently? You can create an equivalent Thevenin source and the resistance for this. This is a VCC and there are two resistances, is that clear? This is a VCC and there are two resistances. So I can actually make a Thevenin source and Thevenin series resistance to that voltage source. The other method which you may solve later, of course I will use Thevenins. Let us say this is IB1 and let us say this is IB2, but this current is the actual base current. So what is the relationship we have? IB1 is IB2 plus IB. Yes. I agree with you, the way it is at the, we are applying at this node the Thevenin's point, okay, at this node. So a loop as if is only on this side, is that correct? The mesh is essentially on this side. I agree with you, but during whatever I put it, when I calculate the currents, that value will be taken care through the RE and other VB values. So I will find what equivalent voltage I am going to get at the actual VB value I am going to get. I will evaluate that VB finally anyway. I will first get a V Thevenin, and from there I will get VB value, which is what exactly I am getting. Okay, so as long as I get that value, that's what I am trying to say. Different methods will lead to a small variation. So one of this is, if what is the current in IB1 will be VCC by VB divided by IB1, is that correct? This voltage minus this voltage divided by RB1 is IB1, VB upon RB2 is IB2, VB upon RB2 is IB2. So I know these two current in terms of VCC and resistances, but I do not know IB right now, okay, I do not know IB. But I have another equation. If I look at the outside, what is the other equation on the output side? VCC is ICRC plus VCE plus how much? IE. But IE, IB and ICs are related various ways. One of course is this, which you can use if you wish any time, or IE is equal to beta plus 1 times IB and IC is beta times IB. You can use any of these expressions, okay. IC is beta times IB, I is beta plus 1, or we can also say I is IB plus IC. Okay. Now one can see from here, what if there is a current flowing here, okay, is V will be now, normally if source is emitter is grounded, there is no voltage drop, we said this is grounded, but now there is a resistance here, current is flowing. So this VE value will be how much? IERE. So VE, how much is this voltage then will be? IERE plus VB on, is that correct? And if I am evaluating a VB from this side as well and I equate them, is that clear? So I will be able to get the exact value of IB I am evaluating at that point for a given VB. VB I am fixing from where? IERE plus VB on is VB. So I have now two equations to evaluate VB, equate them and I can then be able to get the IB value, and therefore once I know IB, IC is known, I is known, I know everything else. Is that clear? So the tricks of the trade is, one method is use this technique, use this equation and substitute IB in terms of IC or IEs, okay, or convert everyone into IBs, whichever way it is, and solve for equations. Is that correct? But there is a simplified method I can give you, which is called alternate method. Instead of even doing this, if you say your beta is very high, how high? Say 100 plus, 200, 150, 100 or plus, at least 100 or more above. How much typical IC you can get? Let us say VCC is 5 volt. How much IC you expect? By highest of IC? VCC by RC. So let us say RC is 1 kilo ohm or 5 kilo, whichever, let us say 1 kilo ohm. So 5 by 1 kilo ohm is how much current I can flow? 5 milliamps. So the maximum current I may flow for a 5 volt supply with RC of 1K is 5 milliamps. That divided by 100, how much it will be? 10 microamps. If IB1 and IB2s are at least one order or two order, means how much? 10 times is one order, 100 times is two orders. If IB1 and IB2 are at least an order or above two orders more than IB, I can neglect IB. Is that clear? I can neglect IB and solve. So every time you need not do long calculations. If your beta is given large enough, but only thing in this course, don't do right now saying that I forgot and left IB, no, right now you assume it, solve it value, you will automatically see that value is small enough. But for quick calculation people say how much, so I can tell you how much because IBs will be smaller. So this current IB1 will be then equal to IB2 and solve, that is the divider, okay, that is the simplest divider. So I know VB without much thinking, is that correct? This is what when you do in the lab, when you go to the lab and let us say you are biasing, you need not worry too much about IB that time, just choose R1, R2 for a given VB you are looking for, is that correct? May not be exact, but that is not needed because in numbers 10.001 is irrelevant, okay, 10 is as much as 10.00, but 10.1 or 10.15 may not be different, I mean they should not be said they are no different, there is a equivalence change and therefore when to leave some things has to be verified, is that, so I gave you some idea, if betas are higher IB1 is equal to IB2, just resistor ratio is good enough for you, is that correct? This is what actual circuit designers do when they are on the board, okay, they just connect them and they say oh it's coming. Why we are allowed to do this? Because we are not interested in VCQ or VBEQ or ICQ exactly. What do we want to confirm? That device remains in active mode. If it is 5.5 or 2.5 or 2.6 or 2.4, how do I damn care for, as long as I am within that. So even with this calculations, if I get value of VCQ, ICQ good enough to remain in active mode, I have no compunctions, I do not worry on those, is that clear? So when you go on the, I hope you have started your lab and some experiments have been performed, when you do amplifier designs, hopefully you will, then you must, someone ask you, your TA may not be knowing, but tell TA, this is very easy sir, you also learn from me, okay. Okay, quickly, if I do Thevenin's equivalent, VTHV RTH at the base for R1, R2, this I am calculating for this RB1, RB2, okay. Now if I do this, can you suggest how much would be VTH? बोलो भाई, ये तो डिवाइडर ही है ना, RB2 divided by RB1 plus RB2 into VCC, and how much is RTH? Short the source, okay, short the source, these two, if you short this, RB1, RB2 are in parallel, okay. So if I now substitute this equivalent circuit, is that point clear? What did I only applied for the biasing network, a Thevenin source and Thevenin's equivalent of a circuit, is that clear? Last people, is that clear? Simplest, this is only representation of bias network as Thevenin source plus Thevenin's resistance. If I do so, or maybe we will draw the other circuit right here, so that RTH, VTH, and then from here you have a standard resistance RE, RC, this is your VC. This value is known to us, so this current is IB, okay. I will give some values and solve for it, okay. Now in circuit I know this, if I am given RB1, RB2, I am given RE and RC, what values I will be given? They are designed, either the values of resistances will be given, then I can find the operating point. If I am given an operating point, then I will not be given RC and RB and I will have to evaluate by design inverse operation for the same, is that correct? What is the difference between analysis and design? I repeatedly saying, if the values are given, when you solve for final operating point, we say you have analyzed the circuit and got this operating point. But in real life, What is fixed important for you? Not the values of resistances or capacitance. We are interested in operating point. We know this is the point I want to operate at. If I want to operate at this point, what should be those values? This I will call it as design. Is that point? The inverse of that is design. If you go down from top to bottom, you say you analyze. Okay. This course is mostly analysis. Sometimes I will show you the design aspect of the circuit. Okay. So I solved this. Maybe if you are noted, I will just give you some values. I have chosen. Okay. These values are not again very sacrosanct, but taken from a book, though this is a unsolved problem in I don't know one of the book, old notes I checked, so but these are unsolved problems. So I solved for my own sake whether I still do it or can do it or not. Okay. Hopefully I am able to do it every time I choose a problem. Okay, sorry. So I calculate VTH, which is 12.2 upon 56 plus 12.2 into 10 volt, and that comes out to be 1.79. What is the formula given? RB1 upon RB2 upon RB1 plus RB2 times VCC is the Thevenin source, so that is 1.79. RTH, parallel combination of RB1 and RB2, that I evaluated as 10K. So here is my circuit finally, which you should look. 10K, Thevenin source, VTH is equal to 1.79 volt. Okay, then this is my IBQ, this is my transistor, this is my 400 ohms, this is my 2K, okay, and this is my VCQ. So this is the equivalent circuit. Equivalent still not done very much because we are not interested in small signal. So we need not expand this transistor area, this into equivalent small signal. Is that point clear why I did not draw the small signal of transistor? Because I am only looking for DC values. Is that correct? If I am looking for AC values, then what should I do? First I should break this into RBB dash everything which yesterday we did and then solve the circuit. Is that okay? In this we have not done that because we are not interested in GM or this value right now. So we are only looking for DC. This value is VB on, which is 0.7 volt. Abhi, please remember IBQ dash into 10K plus I into 400. Is that okay? So I would say VTH Q is 1.79 equal to IBQ into RTH plus VB on plus I into R, rather IEQ now. Okay. How much is IEQ I said? In terms of IB, beta plus 1, beta 0 plus 1. Is beta 0 is same as beta? For all practical purposes, yes. Otherwise, I must specify beta DC independent of AC beta. Okay. Okay. Now using this equation, I have evaluated IBQ. So substitute IEQ by IBQ here, RTH I know, this I know, this I know, this I know. So I calculate IBQ as 21.6 microamps. Correspondingly, ICQ is beta times 100 times 21.6 microamp, which is 2.16 milliamp. and if you wish I can also calculate IEQ multiplied by 101 instead of 100. This is 2.18. Just to get an idea, now let us calculate first the VB or VCEQ. How much is VCEQ? बोलो भाई इक्वेशन बोलो अभी. VCC minus ICEQ into RC plus IEQ into RE. RE, IEQ, ICQ are evaluated, RE, RC are known, VCC is known. So this value I get 4.8 volt. So what is the operating point for this? How do I specify operating point? ICQ is 2.16 milliamp and VCQ is 4.8 volts. What is VCC value? 10 volts, okay, or how much? I said 10 volts. Are we close to half? So obviously these values must be concocted by me so that I come close to VCC by 2, okay. I mean, or the inverse way I did, I find where should be I close to that, okay. So is that correct? The choice of RC, RE, RB1, RB2 should be such that you come close to 50% of the VCC. Please remember this is not exact 50%, less than 50%. It can become 5.2 also or 5.4 also or 4 also, just 4. Even 3.5 is good enough, less, because VC will be in linear when it will be less than 0.6 volts. Anything less than 0.6 or 0.7 volt, VCE is now in saturation, device is getting saturated, is that correct? So as long as you are less than diode drop, you are not in saturation, is that correct? So you can be safe, as long as it is more than 1 volt, you are still in active mode, but there the swings are very small because you are very at the smaller characteristic ends, okay. So you should go little ahead, so around 3, 4, 5, 6 is good enough. Too large RC, what will it, too large this, what will it create problem? Let us say I choose 8 volts, what will it means? No, just think of it in that characteristics. RCs should be very small so that the current, because now you are looking for this point at much higher value, so where it will actually hit very high base currents, is that correct? At those currents the maximum current which device can supply from the power supply is not available to you. So RC will require say 10 ohms, okay. So the power dissipation will be so high that your circuit may not function, is that correct? So too much VC is also not good, too small a VC also not good, so halfway is what you should look, is that as a decision maker you should decide where you should be around is half, okay. Okay. So this finishes bipolar, this similar things can be done by other, this take IB value also and solve again, leave IB and solve again, and you will find that in all cases these values will be very close. I must tell you, if I leave IB and solve for this, I may get little 4.8, you may get 4.7 or 5, 4.9 or kind of thing, not great changes will occur. So what is the method I am suggesting? If you do rigorously also you will get close to same result, if you do unrigorously also you will get the same result, but then you should do rigorously initially because you are not aware how bad or how good the system given to you, but after an experience you know this is good enough. Okay, so this we start with our first goal of the this, which is MOSFET amplifier. So before looking into other MOSFETs amplifiers which are different kinds, first look for its biasing. I repeat, I keep saying DC first, why? Because DC decides the AC values, small signal values, so first look for DC values. One of the circuit shown here as a biasing you have a, okay, the difference between bipolar and this, the voltages are called VDD, VDS, VGS kind of thing, or VSB. If not stated, VSB is 0. Is that point clear? If not stated, VSB is, what is VSB? The substrate bias or bulk bias is if not stated. So essentially if I am not stating you anything, this is what I am doing. Is that clear? If stated, then you will have to evaluate things. At least what things you will have to evaluate for such cases if VSB exists? The capacitances, those are direct functions of substrate bias. Yesterday we did that, isn't it? Otherwise, for this biasing case, we need not worry because these are DC cases, capacitance do not play any role. So we just look for DC biasing. How much is the gate voltage from this? This is VGS plus IDS times RS. Drop across this plus this, drop across RS plus VGS is the gate voltage. Is that correct? Or in numerical say, given a gate voltage, first it will subtract VGS and the remainder will allow us Vs divided by Rs as your IDS. Is that correct? Is that equation clear? However, how much, since this is a DC case I am solving, how much is IDS? Device is in, assumption is device is in, we want to make it in saturation. So we started, yesterday someone raised an issue, correct, but we wanted it so we assumed it, okay, and see that we do get that, okay. So IDS is beta by 2 VGS minus VT. What is the assumption I am doing in all DC cases? Lambda equal to 0. In small signal also I may use lambda 0, but where I will not use lambda 0? Yesterday I said which case I will not use? R0, because that makes it infinite. Okay, so only for that I will keep lambda, otherwise on analytical solutions I may not use lambda often unless lambda is high, 0.1, then I cannot neglect it. If it is 0.002 or 0.001, I say damn. Is that clear to you? So sometimes you may say, sir, all that big things you talked about lambda and all that, and now you are making every time 0. So this is analytical solution, otherwise it becomes nonlinear situation and difficult to analytically solve. Okay. Okay. So this is beta by 2 VOV square, VGS minus VT is over voltage or excess voltage, overdrive. So VGS is VG minus IDS RS or VG minus beta by 2 VOV square into RS. Is that correct? So if I fix VG and I know how much VOV I normally will operate, for a given value of RS, what I am fixing? VGS. In a way I am fixing VGS otherwise also. From where? If I fix my VOV, what I am fixing? VGS, because VGS minus VT is VOV. If I say VOV is 200 millivolt or 400 millivolts plus VT is the VGS. Is that correct? So VGS can be fixed from varieties of way by actually, right now I should not use VOV, you should write VGS minus VT, take VGS on the other side because it will be two terms VGS. Is that clear? This VGS minus VT will appear from here. This is VGS, a quadratic equation will appear in VGS and you will have to solve for it. Is that clear? In real life. Right now, I would say, okay, the basic idea is I can get VGS of my choice by making a choice of RS and making a choice of VT, and this is always, if I am given a VT, I am given betas, then I know for a given RS what will be my VGS. Is that correct? This RS, we will use this latter and very important, it is called degeneration resistance. RS is called degeneration resistance. This has very important role both in biasing as well as in the amplifier designs. RS is very important parameter. Okay. That is source resistance, which is extra. This is not that RS value which is source resistance of the device. This is externally put resistance which is RS. This is external put drain resistance RD. Now why I am showing you this, the way I am now will start biasing is this. Okay. I have an amplifier which is a common source. Is that point clear why it is called common source? Source is going to be grounded or at least going down, and source is also on the two loops. Which two loops I am talking, two meshes I am talking. Source is on this side and is on this side. Source is available to you on, so it is a common source between output and input. Is that clear? That is why it is given a name, common source. Source is common to output and source is also common to input, and therefore it is called common source. Is that clear? So if I have a common source amplifier, this will look, biasing will be something of this kind. Okay. Do you see it is similar to what we did just now for bipolar? You can see there it was RB1, RB2, here I made it RG1, RG2. It is RS, there it was RE, this was RC, there it is RD. As far as maths is concerned, I do not see anything different from what we did. But what is the added advantage we got here? There in the bipolar, this current and this current, we also have this current IB. Is IG available to us in this? No, because MOSFETs do not have DC currents. So then can you tell me how much is VG? RG2 upon RG2 plus RG1 times VDD is this voltage. Divider, potential divider. Is it okay? Since there is no current here, that is what the case, which case I am now talking, IB0 case, small IB case is same as this case. So this VG is nothing but RG2 upon RG1 plus RG2 times VDD is my VG. Now you see other equations. RD, let us say this potential is VD, so VDD minus VD by IDS is RD. Then RS is how much? VS divided by IDS. Now here also one more advantage, IE and ICs are not same, at least very small change, but there is an IB in between. Whereas in the case of MOSFET, the current in source to drain is same, okay. So IDS is same for source side as well as drain side. So VS upon IDS is RS, VD minus VD upon IDS is RD. What is the actual transistor current? Beta n by 2 VGS minus VT square or beta n by 2 VOV square. This is the drain current, IDS current for the transistor. I know this, if I know this, and if I am not given this, I must be given VD or VS. If I am given this, I know the value of RD and RS, or given value of RD and RS, I will be able to get VD and VS. Okay, so let us do some calculations. An example given from Cedra Smith and me. Okay, here is the problem. Please, this is very relevant for us because this is what we are going to use often. We have an example of same transistor biasing, MOSFET, which is N-channel MOSFET. Unless stated otherwise, all MOSFET I am going to use NMOS. Otherwise, I will specifically say it is PMOS. Otherwise, all transistors are used in this are NMOS. Beta N, so even if I do not put N word there, assume beta N, okay. Given to me is beta N. What is beta N actually in numbers? Beta N dash into W by L of the transistor. So right now sizes have been taken, mu Cox is known, and the total product of all that mu Cox W by L is 1 milliamp per volt square. Let us say the bias current I am looking for is half milliamp. Bias current I am looking for is half milliamp. Assume right now lambda 0, VDD is 15 volt, okay, VT is 1 volt, okay, too high value I chose but does not matter because this is given in the book, so I chose the same value. RD is 10 kilo ohms and RS is 1 kilo ohm, okay, sorry it is not 10, it is 1 kilo ohm. No, sorry, both are 10K. Sorry, I am very sorry. Let it be both 10. Okay. Because I get 10 in Yemen. So how much is VDS? VDD minus IDS RD plus RS. In this case, we don't have to IRS or ICRC because IC and I here same. So it is IDS times RD plus RS. So I get VDS equal to 5 volt. VDS equal to 5 volt. Now for saturation, VDS must be greater than VGS minus VT. So VDS plus VT should be greater than VGS. So VGS should be less than 6 volt. Is that correct? For device to remain in saturation, VGS must be less than 6 volts. So let us see now that R1, R2 given to us, whether that gives me VG which is less than 6 volts. Is the criteria clear to you? Given this current biasing for you, I evaluated VDS which is my, what is my operating point? Half milliamp and 5 volt are my DC operating point. VDSQ and IDSQ is half milliamp and 5 volt. Okay. Now for this I want to know what is that RG1, RG2, is that provide VGS which should be less than 6 volts. Is that clear? So let's do that calculations. How much is VG? How much is VG? VG is VGS plus IDS RS. So I substitute VGS plus 0.5 milliamp into 10K. So VGS plus 5 is VG. We also know IDS from this characteristics beta n by 2 VGS minus VT. So I evaluate VGS equal to 2 volt. Is that correct? VGS equal to 2 volt. VG is 7 volt. Please remember how much is VG? 7 volt. Is that correct? This is VGS is 2 volt plus 5 volt. So the how much is the voltage at the gate terminal I am looking DC? 5 plus 2 7 volt. How much is my VGS? 2 volt. Is it less than 6 volt? It is less than 6 volt. So whatever value we were looking for, we have already got now. VGS is less than 6 volt, which means transistor is in saturation. But it is saying otherwise. You assume saturation and you are getting yes, but as long as both sides agree, it's fair enough. It's like a loop. This changes that, that changes this. If stability occurs, the values are okay. Is that correct? It is something like this feedback system. I change that, you change me, but if you stabilize, these are valid on both sides. Is that clear? So assumptions are not very absurd, though initially it looks odd. Hey, you are assumed and you say proved. Obviously. Okay. So for given what is VG value from the network we could find. Please remember what is VG. We said if you see this expression, how much is VG? Rg2 upon Rg1 plus Rg2 times VDD, divider. Is that clear? It's a divider. So if I use this expression, I get Vg is equal to Rg2 Rg1 into VDD. So 7 is Rg2 plus this into 15. I evaluate a relationship, 8 Rg2 is 7 Rg1. Is that clear? 8 Rg2 is equal to 7 Rg1. So I assume one of the values of Rg1 or Rg2 and therefore other is known to me. Using Rg1 and Rg2 values, what value I am going to get? Vg is always equal to 7 volt. For this Vg 7 volt, how much is Vgs? 2 volt. For which my value guarantee that Vg should be less than 6 volt is also met, for which my currents Vgs minus Vt is going to be half milliamp, and for this my VDQ will be 5 volts. So I achieved the biasing by making a choice of Rg1 and Rg2 if given values of Rd and Rs. Is that clear to you? So this is called design. This is a bias network design. Is that design word clear? I evaluated the value of Rg1 and Rg2 for a given, as if I want this. I want ID of half million. I specified you. Okay. Why I am interested in IDQ? What is it going to decide in MOS transistor and small signal? GM under root 2 beta IDS is going to be my GM. So if I fix my IDS, I know how much GM I am looking. GM decides what? The gains. So essentially this IDS choice is the gain requirements. Is that correct? The bias point which I fixed is essentially I am looking at some gains which someone is asking from me to design for. Is that clear? So inverse problem, you got it? Why we do 1 5 this way? Because someone will tell I want a gain of 100, a gain of 100 or 50 or 50. Then I will have to do reverse calculation and see how much GM I must provide you, okay, how much power I will dissipate, so I should not go beyond this wattage. So I will fix some values and start calculating back till I get some numbers of everyone, say okay it will meet all your specs, okay. This is what design is about, okay. So I did this, okay. Before we quit, another biasing which is very important for, normally we may not do this in the case of discretes, yes. Okay, you have a point, because it normally will come in the ratio, okay. Typically it should be Rg1 plus parallel Rg2 should be as high as possible, okay. The choice of Rg1 and Rg2 should be such that their parallel combination is sufficiently much higher in value, okay, typically even mega ohms, okay. Is that clear? The reason why I want that value to be higher will show you in a small signal case, because that source resistance I do not want to use, okay. Is that clear? If that is smaller, then that RS will hurt me here also. But if it comes, I will use it, I don't care if it is smaller, but it should not be very low because it will consume then power at this gate end which I do not want. Is that correct? Please remember, the power is not only on the transistor side but from power supply to the ground through Rg1, Rg2 also is going. So if I choose smaller values, it may still give me a ratio of what I am looking for and therefore Vg may be still correct, but the power dissipation may increase because it is Vcc upon Rg1 plus Rg2, Vcc square upon Rg1 plus Rg2. So I am worried about the power also, which I did not say it, but essentially that decides how much Rg should be kept. If I keep too high in Rg, firstly you cannot get accuracy on those Rgs, no one makes those resistances, okay. So you have a problem, you should be somewhere in between which is available, possible, and something which is good enough for power. Is that correct? And should be large enough compared to the source resistance, okay. ये engineering है, exact कुछ नहीं है, choice करो, okay. There is another way of biasing a transistor, a MOS transistor. Let's say this is the transistor, it's called current biasing or current source biasing. The word which is shown here is this, but what I am really looking for is current source biasing. Yesterday or some days ago I have solved a circuit for you, amplifier, which I showed you this kind of biasing. Do you recollect this amplifier? First day I showed you a MOS amplifier and I say it is biased by fixed IDS. Okay. This is called current source biasing. What is it called? That is the DC current in the transistor is fixed, okay. That is why it is called current source. What is the advantage of current source? What is the resistance it will offer? Equivalent of infinity. इसके across resistance कितना है? Infinite. Why I am worried this is that some people initially R0 they were asking, what is the output resistance of MOS transistor? R0. See, if I see an equivalent, there will be R0 here and the resistance of this, which I call R current source, will be shunted across this RCS. Is that clear? How do I calculate? This is for AC, what is the power supply value we give or what is the status we give to VCC value? For AC, ground. So if this terminal goes to ground, this terminal goes to ground, so these two resistors are in parallel. So do you expect that if this RCS is less than R0, then this R0 has no value because this will going to decide R0. Is that correct? Output resistance of amplifier I want very high, let us say, but this may shunt, okay. So what should be, this value should be higher than R0 or at least R0, that is R0 by 2 at least, then I will get, is that correct? So the current source which I am going to use should have higher resistance of itself, parallel resistance as a Norton's equivalent, is that correct? Now this how do I get is one of the method which I am suggesting to you. Is that clear to you? Okay, let us look at it. This is called current mirror. What do you mean by mirror? If I have something here, it's a mirror and I put something here, I see an image. Optics kiya na humne. So if something in this arm, I know a current, this is my actual device which I want to use as an amplifier. M2 is the transistor which I am going to use as a amplifier. I want to fix this current IDS2 for this, fixed, okay. But I want to see that this current is controllable because bias point must be controllable. So I see I have another current source I put somewhere here which reflects into this. I can change this and then correspondingly this can be changed, okay. But once I fix this, this current is also fixed. This is called current mirror. Is that point clear? This is called current mirror. Now let us see how it mirrors. Let us say I have a power supply, a resistance R and two MOS transistor M1 and M2, and how am I connecting them? The two gates are connected. Is that clear, ma'am? Is that clear? Two gates are connected. But this common point of the two transistor gate is connected to the drain of M1. Is that correct? Is connected to the drain of M1. However, not on this, if I connect then nothing will happen. So this is my actual amplifying transistor and this is my mirror part. There I connect like this. Now since the gates are common, source is common, which is right now connect. Remember, in many times in the transistor theory, VSS may not be 0, it may be minus also, okay. But right now we assume 0, but it can be minus, so VDD minus VSS may actually adds. VDD may be 2.5 volt, VSS may be minus 2.5 volt, so what is actual voltage I am applying? 5 volts, is that clear? Right now I assume VS is 0. Okay, so how much is IDS1 flowing in this circuit? VDD, please look at it, VDD minus the, please remember there is no gate current. So whatever current is flowing in R is same current flowing in transistor. There is no gate current. It is not a transistor biasing, base current is not exist. There also we will neglect, in case of bipolar mirrors we neglect that. But assuming right now MOS transistor alone, so there is no gate current, so this current is 0, so whatever current is coming from here is going down. So this current is VDD minus VSS minus, please remember how much is this voltage? VDS, but since this point is connected to the gate, so it is VGS1, is that point clear? VGS1 is also VGS2 and VDS1 is equal to VGS1, the way I have connected, is that clear? Please remember this point is the VGS1, but this point and this point are same, so VDS1 is same as VGS1, I am shorting on this side, is that correct? So VDS1 is equal to VGS1, but VGS1 is also equal to VGS2 because we are also connecting the gates, is that clear? So that is also equal to VDS1, okay, but I do not know VDS2 right now, I know only VDS1 is equal to VGS1 equal to VGS2, this is guaranteed by me by connecting like this. Since VDS1 is same as VGS1, since VDS1 is now equal to VGS1, it is larger than VGS minus VT, so transistor is in saturation. So your one worry all the time whether transistor is in saturation is met, okay, is that clear? Transistor is in saturation. This mirror is most important in all integrated circuits, okay. Okay, so what is the current in the transistor? Beta N1 dash W by L into 1 VGS minus VT square, assuming lambda 0, which is what I started with. What is the current in the second transistor? Beta into dash W by L2, size of the second transistor, ratio of size W by L, VGS2 minus VTN square. Is that correct? Simple MOS currents are given for both transistors. What is the conditions we are looking into? Beta and dash is same for all n channel transistors. Is that correct? Mu and Cox is not different from different transistors. So beta and dash is same. So these are same. W by L may not be same. M1 may have a different W by L and M2 may have different W by L. Size may not be same. However, VGS1 is equal to VGS2. Is that clear? VGS1, they are actually connecting gates. So VGS1 is equal to VGS2. This is same, VTs are same, this is same. So if I take a ratio of IDS2 by IDS1, what is the IDS2 current? Yes. Transistor in a technology will have same thresholds. Is that clear? Unless substrate bias is provided for a specific transistor, its VT cannot be modified. Is that clear? All n channel transistor will have, unless stated otherwise, will have same VTs. Okay, or at least VT0 will be same. Okay, is that clear? All p channels may have a different VT, but will also have same VTs. Since you said it, yeah, there are new circuits in digital where we are using multiple VTs, but in analog no one has done so far. Okay. So this is common, these are equal, these are equal. So the ratio of IDS2 by IDS1 is how much? Equal to W by L of 2 divided by W by L of 1. Is that clear to you? W by ratio of sizes. So let us say I want IDS2 same as IDS1. So what should be the size of M2, the main transistor? Same as M1. Okay. Or so I must know at least M1 size. Okay. I must know M1 size, then I know my M2 size for the ratio I am looking for. If I want, why it is called mirror? The word given was, if IDS2 is same as IDS1, then same current which I have a reference is now given to the biasing current. Is that why it is called mirror? The current in my M1, which is called reference current, which I am fixing, is same as what is in the M2 or in proportional to that, twice, thrice ratio of W by S. Is that clear, ma'am? This ratio may be 2, 3, 4. So if it is 4, then 4 times the reference current I am biasing at the main transistor. Why I want this game to be done? Because I may choose smaller reference current for different circuit transistors, amplifying parts. I may actually bias them at different bias currents. Is that correct? Let's say in differential amplifier, we will see next time or next time, whenever you, there the bias current will be different, and a common source amplifier may have a different source current, a bias current. So we must have one generation of current source, which multiples of that can be given to different parts of the circuit. So this gives you, allows me to do that. Is that correct? However, I know IDS1, which I call my reference, which is VDD minus VGS1 minus VSS, which is equal to beta and W1 by this. Since I know all the values here, I will be able to evaluate the reference, given a reference current, I will be able to evaluate VGS, and therefore I know what exactly is the values I am choosing R for that. Once I fix my R, I know my reference current. If I know my reference current, I know proportionately the output current or the main transistor current which is being biased. Is that point clear? So why it is called mirrored? Because whatever in reference is mirrored to, okay, another interesting circuit which I didn't show, maybe interest for something. I can do something like this. I have another transistor here, okay, and extend this here, and what will be current in IDS3? No, W by L 3 by W by L 1. Is that correct? So now that's what I say, if I choose a choice different, the proportional current in different arms I can keep changing. Is that clear? This is multiple areas can be given current from same source, and this is a good current source because this I have saw to it that this R I have adjusted such that this acts like a good current source. Okay, that we will see next time how to make this as a good current source. They will be, because these currents which I am using are ensuring same VGS values. Reference is the first one. The other one will be, because biasing is done by current now, not by VGS. Current is proportional VGS minus VT. So I fix the current I get into VGS, which means saturation. Is that correct? That is the way I am doing now. Okay. This is done in where integrated circuits, not discrete. Okay.